Hello everyone. Welcome to this module of the Generative AI course. In the previous session, we looked at how to train a generative sampler using the variational divergence minimization algorithm. We also looked at a special case of VDM methods, which was called the generative adversarial network. In this session, we will continue from there, and the objective of this session is to look at some of the improvisations over the naive generative adversarial network. I will also discuss a couple of famous applications of generative adversarial networks in tasks like domain adaptation or distributional transformation and so on. Okay, that is the objective of this particular module. So let us start this module. So here, the first thing, just a quick recap of what we were doing. So in the generative adversarial network, which is a special case of variational divergence algorithms, so we had two neural networks. One we called the generator network, and there was a discriminator network. The idea is to start with an arbitrary random variable and use a neural network to transform it to random variable of interest by minimizing a distributional divergence metric. So we used F divergence as the distributional divergence metric, and minimizing the F divergence directly is not feasible. Therefore, we constructed a lower bound on the F divergence, which turns out to be this particular objective. So we optimize, we minimize for that lower bound. And while constructing the lower bound, the construction of lower bound itself involves an optimization problem, which is solved over the class of functions, which is represented by the discriminator network. Okay, so we alternatively solve a maximization problem, which is finding the lower bound on the F divergence, and then once we construct the lower bound on the F divergence, we minimize that and we alternate between these two optimization problems. Right, so this is the broad description of what we saw so far. Okay, now I would start today's module by giving you another interpretation of the generative adversarial network as classifier guided generative models. So let us interpret interpretation of a GAN as classifier guided generative samplers. Okay, now what we saw so far was that a GAN was a special case of variational divergence minimization algorithms, where we start with an F divergence, construct a lower bound on it, and then optimize for it. Right. So this is another interpretation of a GAN as a classifier guided generative sampler. So let us look at it. As usual, what we have is a data set with n samples of data, which are drawn IID from PX. This is our as usual setup. Now we also have this sampler, which we are calling as the generator, which would take samples from an arbitrary distribution like a Gaussian distribution, take samples from a normal distribution g theta of g, and we get samples from the output of the generator network, which we designated as p theta of x. Okay, now the goal is to, what is our objective? Our objective has always been that we want p theta of x cap to be close to px, or rather we want p theta of x to be equal to px, and we do it by minimizing the F divergence. We know that interpretation of a GAN, right? Now let's say that there exists a classifier. Suppose there is a classifier, there is a binary classifier such that, now let's call this as dw, the classifier as dw. So we have dw such that dw is 1 if x is coming from p theta, let's call this dw of x, and it is 0 if x is coming from, okay, so maybe the other way around, it's easy to interpret it that way. Whenever x is coming from px, this classifier will give 1 as the label, and whenever it is coming from p theta, this classifier is giving 0 as label. So now dw is a binary classifier, between the samples of px and p theta. So let's say that we have a binary classifier that would classify between the samples of px and p theta. Now the question is, so let's say that the question that we would want to ask is the following, that can dw of x, which is the classifier that we just described, be used for making p theta and px close to each other, right? So the question that we would want to ask is, can we use this classifier to make p theta and px close to each other? So it turns out that a classifier can be used for making p theta and px closer. So let me write the classifier here. Let's say that we have this classifier, which is a binary classifier. We have a binary classifier. So this would take x or x cap both as input, right? dw of x or x cap, and what this would give is 1 if it is x, 0 if it is x cap. So this is the classifier that we have, right? Now the question is, can this sort of a classifier be used to make px and p theta closer? Okay, it turns out that it can. So the answer is that, suppose you have a classifier, okay, now let's say that, so tweak theta, okay, which are the parameters of g theta, till the classifier fails, to distinguish between the samples of px and p theta. Now this can be a strategy that can be used. So what we are saying is, let's say that we have a pre-trained classifier, okay, that would classify, that would give 1 if the samples are coming from px, and it would give 0 if the samples are coming from p theta. What am I saying is that one should keep changing the parameters of the generator till this classifier fails to distinguish between samples of px and p theta. So think about it. When does the classifier fail to distinguish between samples of px and p theta? It's when one of the cases when the classifier would fail is when px approaches p theta, or rather p theta approaches px, because if p theta becomes same as px, then the samples from px and samples of p theta becomes indistinguishable, and therefore the classifier fails. Okay, so now, but the thing is, while I said that one of the failure cases of classifier is when px approaches p theta, classifier failing need not imply px being close to p theta. The converse is not true. So what does that mean is that, however, However, failure of the classifier does not imply or need not imply the distributions matching, okay, px being equal to p theta. So why is that? Let me just show you a pictorial example. Let's take the counter example to show this. Okay, let's look at a counter example. So let's say that our data is in 2 dimensions. Okay, this is for ease of understanding. Let's say that we have our data in 2 dimensions. So this is the space in which the data lies, and I would say that let's the data is distributed this way. So let's say that this cluster represents data from px, okay, or rather let's say that this represents data from p theta, and we have the data from px represented in using this particular cluster. Let's say that this data is from px. Okay, we have the crosses and dots. Dots represent data from p theta and crosses represent data from px. Okay. Now let's say that there was a classifier. So this was the classifier that was initially there. So let's say that this is let's call it DW1, which is the classifier that we had. Okay. Now what we are doing is we are tweaking the parameters of theta, okay, such that this classifier is failing. Now what do you mean by changing the parameters of theta? As one changes the parameters theta, right, this cluster moves around, right, because if one changes theta, p theta changes and this moves around. Okay. Now okay, so let's say that this is being sampled from p theta. Yeah. Now when we change our theta such that this classifier fails, all that the optimization changing theta should do is move this cluster, right, somewhere here. Okay, let me call this p theta 1 for the first set of parameters, and this shall be p theta 2 after we say that, okay, we want our classifier to fail to distinguish between px and p theta 1. So note that the way this binary classifier is working is all the samples that are to the left or above this particular line, okay, given by specified by this classifier belongs to one class, and everything that is below this line or to the right of this line belongs to the other class, because it's a binary classifier. Now when I request my optimization problem to change the theta in such a way that this classifier fails, it's very easy for the optimizer to push my theta in such a way that all the data that was coming from p theta 1 is just moved to the other side of the classifier, so that the classifier fails, right? When the data comes to this side, right here in this scenario, for this scenario, the classifier fails to classify. Rather, I should say the classifier DW1, the particular classifier that we have DW1 fails here to distinguish between p theta 1 and p theta 2. Okay, so this means that when my px overlaps with p theta, we know that the classifier would definitely fail. But classifier failing, this does not imply p theta to be, rather, okay, I'll have to say that this does not imply that p theta is matching with px, right? So now this is the counter example where you can make your classifier fail even without making px and p theta to be the same. Okay, now what do we do? So now this algorithm that we just saw, right, you to keep tweaking your theta till the classifier fails to distinguish between samples of px and p theta no longer holds, because one can make the classifier fail, okay, in spite of p theta and px not being equal to each other. Okay, so now how do we solve this problem? The final, one way to solve this problem is, therefore, hence, the classifier has to be simultaneously tweaked or changed, along with the generator. Right? So now all this analysis that we did was for the case where the classifier was fixed. Now let us not fix the classifier. Let's say that our classifier can also be tweaked. So now what will happen? Let's come back to this diagram. So now when we have our classifier, when we have the flexibility of changing our classifier to, then what might happen is that once we move our data to p theta 2 from p theta 1, what we can do is we can simply change the classifier as well. The classifier can be this. So let us change the classifier and call this dw2. Now under dw2, the classifier dw2 does not fail to distinguish between px and p theta 2. Right? So now p theta 2 has to be moved again to some other place to ensure that the classifier dw2, so let's call this new cluster p theta 3. Okay, so from p theta 2 the data has to move to p theta 3 to ensure that the classifier dw2 also fails. Okay, so this is the idea, that one would keep alternating between a classifier. Okay, maybe I'll just take this down because this might be confusing. Or maybe I'll draw the coordinate axis in a different color. Let me just do that. So let's say that we have this is the coordinate axis, right? So let me call this, we have a two-dimensional feature. This is x1 and this dimension is x2. Our data x now is in R2. Okay, so every xi here has this particular form, that it is, so every data point xi now has this particular form. It is a tuple of two data points. Call this x1i and x2i. Okay, so we are talking about two-dimensional data. So the idea is the following, right? So what we just said is that suppose you want to make p theta close to px, you can use a classifier to do so. The idea is to build a classifier that would distinguish between samples of px and p theta and keep tweaking the parameters theta till a point where the classifier fails. Okay, now we saw that if you fix the classifier, then it is very easy for the optimization to simply find out a theta such that the classifier fails but p theta is not equal to px, right? So when the distributions become equal to each other, the classifier would definitely fail. However, classifier failing does not mean that px is equal to p theta. Okay, so now what is to be done is that one does not have to just keep tweaking theta by having a fixed classifier. The idea is to keep moving the classifier as well, such that every time you move your data, so from one point to the other, till a point where p theta gets overlapped with px, such that there is no classifier that can classify between these 2 points. That is the idea. Now one might get this question that the data, okay, or the generated data or p theta, this cluster can keep alternating between alternating between multiple points, and the classifier of one, there can be a classifier that would fail for one particular configuration of p theta, and then to make sure that that classifier does not fail, you move your p theta to a different location, and the classifier gets alternate to the previous location, and this can get stuck for eternity. This is a possibility. Okay, this is what is called as the mode collapse problem in GANs. Okay, where the optimization problem that we are solving, which is the min and the max problem that we are solving, would not get to a good saddle point, that your p theta may not get overlapped with px at all. So that's a possibility, right? So that is why that's one of the known failure modes of GANs, where so you start with some p theta, okay, then there is one classifier that is there, and now you want this classifier to fail. Move this p theta 1 such that this classifier fails, and you move it to this point. Okay, this classifier failed. Then you learn another classifier, okay, dw2, and now you want to move your p theta 2 such that this classifier fails. Now your algorithm can just put your theta back to this particular place, okay, where both of these the second classifier also fails. Now you change your classifier again to ensure that this fails, and it will come back to this p theta 2 and keep alternating between p theta 2 and p theta 1 and never approach px. That's a possibility. Okay. If you translate this idea to the variational divergence minimization framework, what we are actually saying is that we are alternating between constructing a lower bound on the F divergence and minimizing this, right? The lower bound that we are constructing is similar to learning this classifier. Okay, so the tighter the lower bound that we construct on F divergence, the better this classifier is going to be, and the better the minimization of the F divergence is going to be. However, practically speaking, it is very much possible that the lower bound that we construct on the F divergence, or the classifier that we are learning, is very weak, in the sense that when the minimization of that weak lower bound that is constructed may not make the generated data p theta 2 come anywhere close to the true data px. Okay, and it can keep alternating between different kinds of saddle points, okay, which are not making my p theta and px close to each other. This is a known failure case of GANs. Okay, so please keep this in mind. However, the idea here is that we not only change in the classifier guided interpretation for a GAN, what we are doing is we are not keeping the classifier fixed, but we are also retraining the classifier simultaneously along with the generator. So that is the idea. Okay, so now with all this, let us formulate the cost function with this interpretation. So formulation of classifier guided sampling. So we are formulating a classifier guided generative sampler. Now suppose dw, as I said, is a classifier. It's a function that would take samples from x and maps it to 0 and 1. So it can give a real number between 0 and 1. Now we'll say that let dw of x represent the likelihood of the sample x, coming from px. Okay. So now in our case, this dw is a neural network. It will just give you the likelihood of, we want that to represent the likelihood of the sample x coming from px. Okay. Now log of, so we know that the objective is to maximize the likelihood of the sample x coming from px. So now we want to find our w, okay, such that the objective is, okay, so let me rewrite it. the objective is to maximize the log likelihood of x coming from px. So for any classifier, right, the objective is to maximize the likelihood of data coming from the distribution, right, distribution of interest. That is the objective of any classifier. So we want our classifier to be learned in such a way that we just want to maximize the likelihood of the data coming from px. Okay, so what we want is our w star for the classifier has to be such that we maximize the likelihood of obtaining the data from px. Okay, so that's how we will train the classifier. Now, since this classifier also sees sample from x cap, okay, we want, what is this? This is maximize the likelihood of x sampled from px. This is what this objective is doing. Okay, there is another objective that we would want to optimize, which is we also want the classifier. So classifier should also maximize the likelihood of x cap, okay, not coming from px when x cap is sampled from p theta. So what does this mean? The classifier has to also maximize the likelihood that x cap does not come from px, okay, whenever it is sampled from p theta, obviously, right? So how do we write that mathematically? Now, if dw of x represents the likelihood that x is coming from px, then 1 minus dw of x cap would tell you the likelihood that x cap is not from px, right? So what is this? This is the likelihood that x cap is not sampled from px. This is that likelihood. Okay, what do we want to do? We want to maximize this as well. So we want the log likelihood of this under the expectation, whenever the expectation is now taken over p theta, right? Because whenever the samples are drawn from p theta, we want the log likelihood of those samples not coming from px to be maximized, right? So that's what the classifier is. So now we want our w star also to maximize this particular likelihood, which is the average or expected log likelihood of x cap not coming from px whenever x cap is sampled from p theta. Okay, so now basically what we are saying is, what is this? Let me write this. This is maximizing the likelihood of x cap not being sampled from px, okay, whenever it is sampled from p theta, right? So we want two things to happen for this particular classifier, that assuming that dw represent the likelihood of a sample x coming from px, we want two things to be happening, that whenever the sample comes from px, we want the log likelihood of that to be maximized, right? So we just take the expected log likelihood of dw of x whenever the samples are coming from px, and we want that to be maximized. Okay, so I can write this as whenever x is being drawn from px. Okay, now we also need, note that this dw also takes x cap as input, where x cap is coming from p theta. Whenever x cap is drawn from p theta, this dw of x should give us 0, right? That is how we have designed our dw, which means that it has to maximize the likelihood that x cap is not from px. Okay, whenever it is coming from p theta, we represent that as the expected value of log of 1 minus dw of x cap whenever x cap is coming from p theta. So 1 minus dw of x represents the likelihood of an x coming from px. 1 minus dw of x cap would represent the likelihood that whatever this argument is x cap is not from px, and we want that to be maximized whenever my x cap is actually not from px, or rather it is coming from p theta, right? So we want these two objectives to be satisfied whenever we are learning w star. So let us combine that. So the final objective for the combined objective for the classifier training is as follows. What do we need? Whenever the samples are coming from px, we want that objective to be maximized, the log likelihood to be maximized. And whenever the samples are not coming from px, or rather they are coming from p theta, we want the log of 1 minus that particular likelihood to be maximized. Okay, this is my final objective. So what do I need is that I want, whenever my samples are coming from px, the log of that particular likelihood has to be maximized, and whenever the samples are coming from p theta, the likelihood 1 minus the log likelihood of that particular thing has to be maximized, right? So we want my w, the classifier, to be such that this objective is maximized. W star has to be such that this particular objective has to be maximized with respect to w. So one can very easily note that this is nothing but the lower bound that we constructed on the f divergence, right? So this is the lower bound that we constructed for the f divergence. So let us call this j theta comma w. Okay, now what is the objective for the generator? Now the objective for the generator network, or the g theta network, is such that the classifier has to fail, right? That is the way we have, such that the classifier has to fail, right? We have to tweak our theta in such a way that the classifier has to fail. Now how do we do that mathematically? That we simply invert the optimization problem that is for the classifier. That's all. Invert the optimization for the classifier. If we do that, then we will ensure that our theta will be such that the classifier objective is inverted. So what do? We just minimize the classifier objective with respect to theta. Now while the classifier is trying to maximize a particular objective with respect to its parameters, we will just minimize. What do you mean by inverting? Change the optimization problem from maximization to minimization, that we find out the generator parameters simply by minimizing the classifier objective, right? So finally what happened is that we get our theta star and w star, which are the generator and the classifier parameters, such that you have one objective function and the generator is trying to minimize that objective function, and the classifier is trying to maximize that same objective function, right? And what is this objective function? This objective function is trying to classify between the samples of px and p theta. Whenever the samples are coming from px, it is giving you 1, and whenever the samples are coming from p theta, it is trying to give 0. What we are doing is we are trying to find the generator parameters such that the classifier fails, and we are trying to make the classifier learn the decision boundary such that the generated samples are being able to be distinguished from the true data, right? So there is an adversarial game that is going between the classifier and the generator, and hence the name the adversarial networks, right? One of the reasons why this is called the adversarial networks. Already told you why this is called the adversarial networks, because what we are trying to do is trying to solve a saddle point optimization problem which involves one objective function and two set of parameters. While one set of parameters is being chosen such that the objective is being maximized, the other set of parameters are being chosen such that the objective is minimized, right? That's why the name the adversarial optimization. So I can tell you this. This is the adversarial part. Okay, this is the classifier guided interpretation for the GAN. So note that from mathematical standpoint and what is happening, right, algorithmic standpoint, whatever we saw as variational divergence minimization is absolutely the same as classifier guided training as well, but this is just another interpretation of how one can perceive the naive GAN. Okay, please note that this interpretation is not generalizable across different other F divergences, right? Why? Because for other F divergences, there is no guarantee that the T function that we use to bound the F divergence does not have an interpretation that the T function is a classifier. Only with this particular choice of the F divergence that our T function has a has an interpretation which adheres to that of a classifier, right? And once this can be interpreted as a classifier, one can see this entire process of adversarial optimization as a way to guide the generator or the sampler using this classifier. So what is the story? We want to transform a Gaussian random variable into the random variable of interest, which is px in this case, and we do that via a classifier. What is this classifier trying to do? This classifier is trying to classify between the samples of px and p theta. The moment this classifier fails to classify between samples of px and p theta, we are done, correct? But if you fix the classifier, then it is very easy for the generator to make this classifier fail and still not make px to be equal to p theta. So what do we do is that we not take a fixed classifier but also change the parameters of the classifier along with the generator parameters such that we keep changing, alternating between the classifier and the generator parameters till a point where p theta actually overlaps between px. Now, diagrammatically speaking, what's happening is that we are moving this cluster around, right? I mean, first you have some p theta 1, there is a classifier which is classifying between these two p theta and px, right? And then you move your p theta to some other location p theta 2 such that this classifier fails. Then change the classifier from dw1 to dw2 such that the classifier is again able to classify between p theta 2 and px. Okay, then change your p theta or theta in such a way that p theta 2 goes to p theta 3 such that dw2 fails, and keep doing this. So this is the idea. From an F divergence minimization perspective, what we are doing is we start with some generator parameters theta. Okay, with that we construct a lower bound to the F divergence between px and p theta, and then we change the p theta depending upon that particular lower bound that we have constructed. Once we change the p theta, the F divergence also changes, right? So therefore, we'll have to construct another lower bound between that new p theta and the existing px, and we alternate between these two. So basically what is happening is that start with a theta, construct a lower bound on the current F divergence, and then minimize that F divergence. Okay, in the hope that the minimization would actually make the lower bound, the new lower bound that we construct, a little tighter. Okay, then you change the theta again, construct another new lower bound and minimize that, and keep alternating between these two processes. From a classifier standpoint, move your p theta such that the current classifier fails, okay, and then tweak your classifier such that under the current theta you can distinguish between the real data and true data, and keep alternating between these two processes. Okay, so as you can see, one can get stuck in a place where the classifier keeps fooling the generator and the generator keeps fooling the classifier, so to speak, right? Classifier makes the generator fail and the generator makes classifier fail in the alternate steps, and that is a known failure case of GANs where they can get simply stuck between these two, and you will never reach px by tweaking p theta. That's a possibility. Okay, that's why people say that training a GAN is a non-trivial task. Okay, and it is the GAN table is known to be, sorry, GAN training is known to be notoriously unstable. Okay, so now we will move on to different kinds of improvisations of GANs.